Good morning. Now we are discussing about the linear harmonic oscillator, a particle that executes simple harmonic motion about a mean position. The two along a straight line is called a linear harmonic oscillator. Let us consider a straight line. AB or its boundaries. I fix the boundaries. These are the two boundaries, A and B are the two boundaries on a straight line. Okay, and let O is the midpoint of AB. O is the midpoint of AB. Let us consider a particle on this straight line. The particle is moving from A to B, B to A, and the process will continue again and again. The particle moves between A and B continuously. The motion is from A to B and B to A back. It is the to and fro motion. The motion will repeat itself and it is said to be oscillating about the mean position. And such a particle which is oscillating about a mean position along a straight line is called a linear harmonic oscillator. At any instant of time, the acceleration of the particle at any position, along the straight line is directly proportional to the displacement. The acceleration of the particle at any point, let us consider at point C, is directly proportional to the displacement x. If this is x, directly proportional to the displacement and is always directed towards the mean position. Therefore A is always directed towards the center O, and therefore I take with a negative sign. Since A and x are oppositely directed, the acceleration of the particle is always directed towards the mean position. The acceleration at any point is directly proportional to the displacement of the particle from the mean position. The examples are the vibrations of diatomic molecule, vibrations of atoms in crystal lattice are the examples for linear harmonic oscillator. Now we consider a particle which is executing simple harmonic motion, the two about a mean position along a straight line, in the sense linear harmonic oscillator. And if the amplitude of the particle from the mean position is small, then the restoring force is directly proportional to the displacement of the particle from the mean position, and the restoring force is always directed towards the mean position, and therefore mathematically it can be written as F is equal to minus x. F is the restoring force, x is the displacement. At any instant of time, if the amplitudes are small, the restoring force is directly proportional to the displacement and it is always directed towards the mean position, and that is indicated by the negative sign. Or F is equal to some constant into displacement with a negative sign, where K is our constant. The potential energy of the particle at any instant of time is given by V of x. Potential energy is a function of displacement x, that is equal to minus integral 0 to x of x dx. Substituting for f, we get integral 0 to x kx dx. And on integrating and substituting the limits of integration, we get potential energy as half kx square. Now, let m is the mass of the particle that we have considered, which is exhibiting simple harmonic motion. We know that F is equal to minus kx, but F is m into d square x by dt square. F is equal to ma, but a equals d square x by dt square, that is equal to minus kx. Or rewriting this, we get d square x by dt square is equal to minus k by m into x. Minus k by m into x can be rewritten as minus omega square x, where omega square is k by m. or k equals omega square m. Now, rewriting equation 1, we know that equation 1 is half kx square. Therefore, v of x becomes half, instead of k, I write this omega square mx square, omega square mx square, or omega square is nothing but 4 pi square nu square, and mx square is as it is. Or rewriting again, we get vx is equal to 2 pi square nu square mx square. This is the value of v. The Schrodinger equation in one dimension is d square psi by dx square plus 2m by h cross square into e minus v of psi is equal to 0. Substituting for v, we are substituting this value for v in this equation over here. We get d square psi by dx square plus 2m by h cross square into e minus of 2 pi square nu square mx square of psi is equal to 0. I consider this term as equal to alpha. 2me by h cross square is taken as alpha, and 2m by h cross square into or 2 pi m nu by h cross as equal to beta. We have 2m over here, 2m also here, so it becomes 2 pi square nu square m square x square by h cross square. So I take 2 pi m nu by h cross as equal to beta. Therefore, this relation becomes d square psi by dx square plus alpha minus beta square x square of psi is equal to 0. And I call this as equation 2. Let us introduce one more variable y, which is a function of x and a constant root beta. Y equals root beta into x. Differentiating this, we get d psi by dx is equal to d psi by dy into dy by dx, that is equal to root beta into d psi by dy. Again, integrating one more time, differentiating one more time, we get d square psi by dx square is equal to beta into d square psi by dy square. You can see here. And substituting this value in the earlier equation, in the second equation, in equation number 2, we get beta into d square psi by dy square plus alpha minus beta y square of psi is equal to 0. Or d square psi by dy square plus of divided throughout by beta, we get alpha by beta minus y square of psi is equal to 0. The solution for this equation will be in the form alpha by beta equals 2n plus 1, where n is an integer. Now substituting for alpha and beta, we know that alpha is equal to 2me by h cross square and beta equals 2 pi m nu by h cross. So simplifying this, we get e by pi nu h cross, that is equal to 2n plus 1. Since alpha by beta is 2n plus 1, the RHS remaining the same. Therefore, rewriting, we get E equals h nu into n plus half. H cross is nothing but h by 2 pi. So instead of h cross, I write h by 2 pi, and simplifying, we get E is equal to h nu into n plus half, where n is an integer which can take the values 0, 1, 2, 3. And if we substitute the values for these values for n, we get E different values of energy, that is half h nu, 3 by 2 h nu, 5 by 2 h nu, and so on. And this is E0, E1, E2, and so on. This shows that the energy values are quantized, in the sense the energy values are fixed. The energy corresponding to n is equal to 0, this one is called 0 point energy. This energy corresponding to n is equal to 0 is called 0 point energy. So you can take the difference of these consecutive energy levels, the difference of these two, and so on. If you take the difference of the two energy levels, it turns out to be h nu, and that will be a constant. And so the energy levels are said to be equally spaced as shown in this figure. This is about the linear harmonic oscillator. Thank you.